Okay, we'll get started in just a minute here. Okay, any questions before we get started? Hope y'all had a good Easter. I know some of y'all are traveling right now, so I'm recording this, and I'll give that to y'all later. All right, just give me one more minute. Okay, I'm going to get started. So we are working on a practice 3 for test number 3. That's tomorrow, whatever time you have it. So as before, it's 10 questions. It's usually going to be pretty similar to this practice test that we're working on. So usually the questions will have the same content in the same order. They'll just have like slightly different numbers and wording. So yeah, you'll log in, just have your work on it, and then before it's due, like before the end of the time, Ms. Seats will tell you to like take pictures and submit it. So submit it on Canvas, and then you can leave the Zoom session. So submit it before you leave, just to make sure there's no issues. Okay, about this test specifically, really important is 7 of these questions involve sign charts. So you really need to have sign charts down if you want to do well on this test. You need to understand what they are and how to make them, and make sure you get the right signs and everything. So yeah, questions 1, 2, 4, 5, 6, 9, and 10, they all involve a sign chart. Either you have to make one or you need one in order to answer it completely. So I'll talk about those a little bit. Okay, so as before, I have the question breakdown for all 10 questions. I'm just going to go through that really quick. Okay, questions 1 and 2, these involve sign charts specifically. So question 1, this is a first derivative sign chart. So what it's asking you about is increasing, decreasing, and critical points. These all have to do with the first derivative. So what you do for this problem is just make a sign chart, and then you read off the intervals, and that's how you answer the question. So to make the sign chart for f prime, first of all, you have to find f prime, of course. Then you ask, where is it equal to 0? Those are the critical points. You'll mark those on your sign chart. And then you'll ask, where is it plus or minus? Where is it positive or negative? Those are the increasing and decreasing areas. And then it mentions this first derivative test. So when you get a critical point, you don't know right away if it's at the top, if it's a maximum, or if it's a minimum. And the way you tell is with this first derivative test. So if you're going from increasing to decreasing, that's probably backwards for you, increasing to decreasing, then that's a maximum. If you're going from decreasing to increasing, that's a minimum. So pretty intuitive, but I'll talk about that more in a second. Number 2, this is the second derivative sign chart. So it's asking about concave up and down, and inflection point. These all have to do with the second derivative. So all we do is make a sign chart for it. Where is it 0? You set it equal to 0. And then where is it plus or minus? And so you just determine where it's positive or negative. There are a few ways to do that. Okay, number 3, this is L'Hopital's rule. L'Hopital's rule, very simple. There's a condition for it. You have to get 0 over 0. Okay, so we're taking a limit, right? We plug in, that's first step. If we get a 0 over 0, then we can use L'Hopital's rule. Okay, and all the rule is that we take the derivative of the top and the bottom, and then we plug in again. Okay, so that's the L'Hopital's rule. It says the limit is the same if you take the derivative of the top and bottom. Okay, 4 and 5. These are both about just reading stuff that's given to you. So in 1 and 2, you made your own sign charts. In 4 and 5, they're going to give you sign charts, and they're going to give you tables and limits. And you have to turn those into what it's asking for. So the tables are going to give you points on the curve. So it'll give you like x and f of x. That'll give you points. Limits, these will give you asymptotes. So they can give you horizontal or vertical asymptotes. And then sign charts, they'll give you sign charts for the first and second derivatives. And like I just discussed, those will give you all of these things. So increasing, decreasing, concavity, all that stuff. Number 6, graphing. So this is a fun one. I like pictures. All you really have to do, put down all the data that you're given, put down all the points, put down all the asymptotes, and then you just connect the dots. Okay, so you connect the dots, you approach the asymptotes. So I'll discuss that more in detail. Okay, 7 and 8, these are absolute max and min. So what I mentioned before, that's local, right? So you have the top of a hump or like the bottom of a valley. Absolute, this means the biggest thing, period, like in the entire region, like the highest value and the lowest value in the entire interval. That's what we're looking for. So for both of these problems, first thing, we're going to find the critical points because we're going to need those. And then the whole idea is to test at different points. So to try and find the value at different points and then compare them. So what you do changes depending on if it's closed, that's number 7, or if it's open, that's problem 8. So if it's closed, you just plug in at the endpoints in the critical point. The highest value is your max, the lowest value is your min. For the open, you only look at the critical points. So you don't look at open endpoints, just ignore those. Just look at the critical point, and then use the second derivative test. So if the second derivative is negative, that means it's kind of curving downwards. That means you're at a maximum. Okay. If the second derivative is positive, that means you're curving upwards. You're at a minimum. Okay, that's called the second derivative test, and we'll do that later. Okay, number 9. This is asking about a point of diminishing returns. All this is an inflection point. All this is, just find the inflection point. That's the point of diminishing returns. It's where you go from, like, you're curving upwards, right? And then you start curving downwards. That's what an inflection point is. You change from curving up to curving down. That means your slope has reached its highest, like you're at the highest slope, and then after that, it's kind of leveling off, right? That's the idea. So just find the inflection point. And there's one thing you have to show. You have to show that the second derivative goes from positive to negative, which is just another way of saying that your rate is at a maximum. Okay, last problem, number 10. This one's kind of interesting. It's about optimizing revenue. So there's something that you have to do here that you haven't had to do before, which is to come up with your own variable, right? So usually they tell you X is the number of like ski jackets, right? Or something like that. This you have to come up with your own. They don't tell you what X is. They don't give you any functions. You have to make your own variables and functions. This is just a word problem. So for this, for the one in the practice, like the best thing to do is say X is the number of price increases. We're talking about rent. So if you increase your rent, less people are going to want to stay there. And so that's the idea. And so once you define your own variable, then you have to make your own functions. And then revenue is price times the number of things that you're selling. And then we want to maximize the revenue. So we find the critical point, set it equal to 0, and then we show it's a maximum by showing that the second derivative is negative. So that's the second derivative test. Okay, so that's the breakdown. Let's get started. Hopefully this won't take too long. If you actually look at the answer sheet for this, there's really not much work for you to show. But it's important that you understand everything. So like I said at the beginning, sign charts are a humongous part of this. So 7 out of 10 problems involve sign charts. So make sure you know how to do them. So what are they? It's just asking, we have a function. It's just asking, where is it positive? Where is it negative? Where is it zero? So I have a function here. This is a parabola, right? All I've done is I've labeled it's 0 here and here. So it's 0 at 1 and 3. Okay. And then if we look over here on the sides, so on the left, it's all positive. And on the right, it's all positive. And in the middle, it's negative. Okay. And so what a sign chart is it's basically, we've just simplified this. So we've marked where this function is equal to 0. So it's a 0 at 1 and 3. It's negative in the middle, and it's positive on the sides. So this is our sign chart. So if this was f prime, like if this was a graph of our first derivative, then this would be the first derivative sign chart. If this was a graph of our second derivative, then this would be the second derivative sign chart. All you do is you turn the plus and minuses and put them on this number line. Okay, so there's really just 2 steps here. First one is to mark the zeros. So you find where it's equal to 0, and then make these little tick marks. And the second step is to figure out if it's positive or negative in each one of these intervals. Okay, so in between these zeros. Probably the most straightforward way to figure out the sign is to just plug in different numbers. You have f prime, like so this is f prime. You have this function, so you just plug in different numbers into it. So if I plugged in 2, that's in the middle here, I would get a negative number. Okay. If I plugged in 0, that's in this left part, I would get a positive number. If I plugged in 4, which is over here, I would get a positive number. And so that's how you would determine it. That's probably the most simple way. Another one is to look at the signs of the factors. So this is how Masseet's does it. So for this function, let's see if I can show you. For this function, it has zeros at 1 and 3. This is just the function that I've written here. This is x minus 1, x minus 3. And so what Masseet's does is she looks at the sign of x minus 1, and she looks at the sign of x minus 3, and then uses that to determine what these should be, right? So if they're both positive in one of these regions, you get a positive. If they're both negative, you get a positive. If they're opposite signs, you get a negative. Okay, so that's how Masseet's does it. My way of doing it is to just look at the graph. Okay, so this function, this is something that's x squared, right? This function is x squared. It's parabola. It opens upwards, so I know it's negative in the middle and positive on the sides. So again, I'll show you examples for all these in a second. But zeros and find the signs, and you're going to need that for almost all of these problems. Okay, graphing. I'll come back to this when we get to problem number 6. But this is just for reference. I'm going to send this out later. Okay, so I'm going to get started. Problem number 1. So use the first derivative test to determine the intervals where f of x is increasing and decreasing, and determine any local extrema. So increasing, decreasing, local extrema. This is all first derivative. We're going to use the first derivative here. So all we do is we make a sign chart for f prime. Okay, so that's the objective. We have this function here, this f, and we're going to make a sign chart for it. So first of all, you find the first derivative. So if I take this f, I'm going to take the first derivative. So that's the power rule here. So the first term is going to give me 6x squared. The second term is going to give me 18x. All right, so this is the first derivative. And then all I've done is I've factored it. Okay, so it'll usually help you to factor things out. So both of these terms, I can pull out a 6x, and I'm left with 6x and x plus 3. Okay, so I factored it. Okay, so this is it. This is f prime. And now to find the zeros, we're going to set it equal to 0. And right away, since I factored it, you can see that x equals 0 is 1, and then x equals minus 3. Okay. All right, so you factor it, and then that makes it very easy to find the zeros. Only other question. So I'm going to mark these zeros on our sign chart here. So -3 and 0. The only other question is it positive or negative in these three different regions? And I'll show you my way first. This is my way. So this right here, f prime, it's x squared. So we see this x squared. We have a positive x squared. So that's a parabola that opens upward. This is what it looks like. It has a 0 at -3 and at 0. I'll answer that question in a second. And so because it opens upwards, right? It's positive on the sides and negative in the middle. Okay. If this was a negative x squared, then what we would have here is a downwards parabola. So it would be positive in the middle, negative on the sides. Okay. So I got a question here. Why x equals 0 and not only -3? So when I factored this, so all I did was factor it. Have this term x right here. Okay, so if I have x equals 0, I'm going to have 0 times all of this stuff, which is 0. Okay, so you have to look at each of the terms that have an x in it and think of what can x be to make this 0. So x by itself, that's a 0. X plus 3, so if you choose a -3, that'll make this one 0. So you set each one of these different terms to 0 individually.
Awesome, thank you.
You're welcome. Okay, so anyway, based on my method, just by looking at the picture of this, it's an upward parabola. So that's plus, minus, and then plus. So that's how I would get it. But I'm going to show you how Messeats does it. So aside from just looking at the picture, let me drag this in over here. This is how Messeats does this. And this is what you'll see on the actual practice test on the worked out version. So we have two terms here, 6x and x plus 3. Okay, so the question is, what are the signs of these in each of the intervals? Okay, so 6x. So if I pick a number over here that's greater than 0, 6x is going to be positive. So like what if I picked 1, right? So 6x is going to be 6. That's a positive number. What about x plus 3? So if I pick a number greater than 0, I'll have like, say like 1, right? 1 plus 3 is 4. That's positive. And so really, I'm just building sign charts for each of these terms. Okay. And then they're multiplied together. So a positive times a positive is going to give me a positive. All right. So I do the same thing in this middle interval. So this is between -3 and 0. So if I pick a negative, this is going to be a negative number, right? So if I pick a like -1 and I plug it in here, I'll get -6. So this term is going to be negative. And if I pick like a -1, I'll get -1 plus 3 is 2. So it's positive. Okay. So I'm not gonna do all this work for every single problem this involves, but I just want to show you how this works. So this term is negative, this term is positive. If you multiply those together, you're going to get a negative number. Okay. And then over here, 6x, that's going to be negative, and x plus 3 is going to be negative. All right, so if I had like -4 that I plugged in, I would get -4 plus 3 is -1. So that's a negative number. Okay, so minus and minus makes a plus. Okay, so that's how Messeats does it. You factored it out, you have these two terms, and so you're going to look at these factors individually. You're going to make sign charts for each of the factors. And then when they're the same, you get plus. When they're different, you get minus. So that's all there is to it. Okay. I find it much faster just to know what these, but either one's valid as long as you get the right sign chart. Now, this was the whole goal. Once we got the sign chart, we're good. We can answer the problem. So first of all, I'm going to kind of draw this so that you see what's happening. So this is the first derivative. When it's positive, that means increasing. When it's negative, that means decreasing. And when it's 0, that's a critical point. So I'm just going to draw something on here so that you can really see that. Okay. All right. So what I've done here, when f prime is positive, that's increasing. So I've drawn a line that's going up. When it's decreasing, I've drawn a line going. Hello, can you all hear me?
Yes,
Yeah.
now we can.
Mhm.
That my Wi-Fi broke. So just give me 1 second for it to reconnect. Okay. Okay. Sorry about that. Let me get my screen back up. Okay, sorry, we're back. All right, I'm not sure how much I missed, so I'm gonna go back 1 step to this this drawing, right? Okay, so f prime tells you if it's increasing or decreasing. So all I've done is I've drawn a little picture here. So when it's positive, that means increasing. When it's negative, that means decreasing, so going down. When it's positive, that means it's increasing. Okay, and so just looking at this now, I can write out these intervals. So increasing, that's where it's positive. So the way I write that, all right, so there's 2 different intervals. So there's this part on the left and there's part on the right where it's positive. Okay, so the one on the left, that extends down to negative infinity and it goes up to -3. Okay, so that's how I write the left interval. And since there's 2 intervals where it's increasing, I'm going to write a little U symbol here. It means union. And then I will do this right interval. So this starts at 0 and goes up to infinity. Okay. All right, so decreasing, that's in the middle where it's negative. That's -3 up to 0. All right, local max and min. So this is where this first derivative test comes in. Okay, so we know there are critical points at -3 and 0 just by setting an equal to 0. But we don't know right away if it's a maximum or a minimum. And so just look at this picture here. So if it's going from increasing to decreasing, so going from up to down, then that's a maximum. If it's going from decreasing, that's a minimum. Okay, so top of a mountain, bottom of a valley. So pretty intuitive. So the critical point that we got at -3, that's a maximum. So there's going to be a local max at -3, and then we need this to be a point. So we need to know actually how high this point is. So one way we can do this is we can say f of -3 equals, and then we plug in the value. So that's going to give me a 24. All right, so I plug back into the original function up here, and I'll get 24. So for local maxima and minima, you want to write this as a point. So it needs an x and a y value. So you can write it like I just did, or you can write it as the point -3, 24. All right, same thing for the local minimum. We know from the first derivative test, this is going decreasing to increasing. So that's a minimum. I'm going to say f of 0 equals, let's look back at our function up here. If I put in a 0, I'm going to get -3. So f of 0 equals -3. And another way I could write that is 0, -3. And that should be, yeah, that's what you get on the answer key. Okay, so first derivative, make a sign chart. Increasing intervals, that's just where it's plus or minus. These local max and mins, that's where it's equal to 0. And you use this first derivative test to see whether it's a maximum or a minimum. Okay, any questions on this one? All right, so this one should only take you a couple minutes to do if you understand it. Not a lot to do here. Okay, number 2, we're going to do the exact same thing with the second derivative. All right, so this time it's asking about concave up, concave down, and inflection points. That's all related to the second derivative. So just like before, this is our function. We're going to make a sign chart, this time for the second derivative. Okay, so first question to ask, where is it equal to 0? So we're going to find where it's equal to 0. We take our first derivative, power rule. Okay, so the first term we get 3x squared. Second term we get -2x. And then the derivative of a constant is 0. So this is our first derivative. For the second derivative, we just do power rule again. So for the first term, we get 6x. For the second term, we get -2. And this is our second derivative. All I've done here is factor. I factored out a 6 so that I have just an x by itself. And the reason for that is it makes it very easy to see that x equals 1/3 is the root here. So if I want to make this equal to 0, I just pick 1/3. All right, so that's how I get 1/3. All right, so that's where the second derivative equals 0. So I'm going to mark that on my sign chart right here in the middle. The other question is, where is it positive or negative? So I'm going to show you a different method. Macit's method works. My method works too. But I'm going to show you something else, which is plugging in. So we have 1/3 here. So I'm going to pick things from either side and plug in and see what we get. So second derivative, where do we have it? It's right here, right? This 6x minus 2. Or you can plug into this other one. So if I pick a 1, that's on the right, I'm going to get 6 times 1 minus 2. That's 4. So that's a positive number. So I'm going to get a positive number over here. If I pick a number from the left side, like 0, -2. So that's a negative number. So this is negative. Okay, so that's how you do it by plugging in. You just pick numbers from either side and then see what the sign of the second derivative is. Okay, so my method will look something like this. So 6x minus 2, that's a line with positive slope. So it's going to be negative on the left and positive on the right, and you're done. Let's see, I got a question. Do you plug into the original function or the derivative? All right, so we're looking for the sign of the second derivative. So when you plug into the second derivative. We want to know the sign of the second derivative, right? Later on, when we're trying to get a point, if you're trying to get a point on the curve, you plug into f. But when you're trying to get a sign chart, you plug into the thing you're getting a sign chart for. So in this case, it's the second derivative. All right. So let's do our intervals. So like I had, I'm going to draw another picture here. So negative, that means concave down. Positive, that means concave up. Right. So I'm going to just have these as a picture here. So it's bending downwards on the left and it's bending upwards on the right. And then wherever it switches between these two, between down and up or between up and down, that's an inflection point. So I know on a lot of quizzes, people wrote like no inflection point, but there is an inflection point wherever we switch. As long as there's an actual point here, if this was like not defined, then that's not the case. But this is the point where we switch concavity, so that's called an inflection point. Okay, so let's write out our intervals. It's concave up here on the right where it's positive. So that's 0 to infinity. And it is concave down on the left. So that's where it's negative. So that's minus infinity up to 0. And then
Wouldn't it be 1/3?
Oh yeah, sorry. Thank you. Sorry.
No
yeah.
problem.
So this starts at 1/3. Thanks. All right. So yeah, and then this left interval goes from minus infinity to 1/3. Let's have those both in here. Okay. Sorry if that confused anyone. Okay. Inflection point. So we have this x value, but we want a point, so we also need the y value there. So we say f of 1/3. So we just plug it into the original function right here. So if I plug in 1/3 here, I'll get 1/3 cubed minus 1/3 squared minus 5. And you can do that on your calculator. That's minus 137 over 27. Minus 137 over 27. And your calculator will probably give you something like minus 5.074, right? And either one of those will work. Okay, so that's totally fine way to write it. Or you can write it as a point here. So 1/3 is the x value, and then minus 5.074 is the y value. Okay, so the point here is to have it as an x and a y. So we need the coordinates. Okay, any questions on this one? Which equation do you put in? Okay, so in order to get a point on the curve, you put it in f, right? For the sign charts, you plug it into the function that you're looking at the sign chart. Yeah, you got it. But to get a point for your answer, to get a point on the curve, you plug it into f. All right, so make sure you get that right. All right, so that's 1 and 2. They're both based on the sign chart. Number 3, we're gonna take a step in a different direction. This is L'Hopital's rule.
Could you go back up for a second? Sorry.
Oh yeah, you got it.
That's good. Thank you.
All right, and I'll send this out to everyone once this is done. If you want to check anything else. Okay, so number 3, this is L'Hopital's rule. We're taking a limit. So the limit as x approaches 0 of 4e to the x minus 4 over 3x. Okay, so usually, if you remember from the first help session, we just take the derivative. Or sorry, we just plug in. First thing we do is we plug in x equals 0 and see what we get. So if we do that, I'm going to plug in a 0. So it's 4e to the 0 minus 4 over 3 times 0. Okay, now one thing that's important to know, anything to the 0 power is 1. Okay, so x to the 0, that's 1. E to the 0, that's 1. 2 to the 0, that's 1. So anything to the 0 power is 1. So I'm going to get a 1 here. So I'll have 4 minus 4 on top and a 0 on the bottom. So I get 0 over 0. All right, the point is if I try plugging in my number that I'm approaching, I get 0 over 0. And that lets us do L'Hopital's rule. Okay. And what the rule actually is we take the derivative of the top and the derivative of the bottom and see what the limit is now. So this was our original limit, right? See, it's this fraction. So I'm going to take the derivative of the top here. So the derivative of 4 to the x minus 4, and the derivative of 3 to the 3x on the bottom. Okay. The derivative of the top, we know how to do this. So the derivative of a constant is 0, so that just goes away. The derivative of 4e to the x is 4e to the x. Okay, so e to the x is this special function where if you take the derivative, nothing happens to it. So just remember, e to the x is something that doesn't change. And that's going to be true later on in the class when we do integrals. But e to the x does not change. So the derivative of 4e to the x is 4e to the x. Derivative of the bottom, 3x, that's just 3. And now that we've taken the derivatives, now we plug in again, okay, and see if we get something nice. So if I put in a 0, I'm going to get 4e to the 0 over 3. E to the 0 is 1, so I get 4/3. Okay, so step 1, plug in, I get 0, 0, 0 over 0. Take the derivatives, I get this. And now I plug in again, and I get 4/3. Okay, and this is the answer. So the original limit that we had is equal to 4/3. Okay. All right. So L'Hopital's rule specifically says the limit that we had to begin with is the same as the limit when we take the derivatives on top and bottom. So this right here is the rule. They're the same. What would the derivative be if, for example, the limit was approaching 1? So for this problem specifically, if we were approaching 1, let's see, we would have 4e to the 1 over 3. So that would be 4e minus 4 over 3, and that's not 0 over 0. Right? So if we had this being 1, we would not get 0 over 0, so we wouldn't use L'Hopital's rule. Just for example. But if we were, if it did give us 0, 0, we would get the exact same derivative, except this time we'd plug in a 1. Okay. All right, so get the 0, 0, take the derivatives, plug in again. That's it. Okay, any questions on this one? Do we need to write the full limit at the end to not get marked off? Just to be safe, yeah. Just write the original limit equals 4/3. Yeah, so just write out the entire answer. She's a pretty strict grader. She may or may not count off for that.
If it's asking us to use this rule, do we need to do the first step to show that it's 0 over 0, or can we just assume it's 0 over 0 since it's asking us to use this rule?
I mean, yeah, you can assume that it's going to be a 0 over 0. Otherwise, you wouldn't have a chance to use the rule. I do think she wants you to show this. She wants, I think, or at least on the quizzes that we had, she wanted you to show that it was in fact 0 over 0, and so that you can use the rule, because otherwise you can't, right? So there's a condition on it. So if you have the time for it, just plug in and get the 0 over 0, and that'll make her happy. It won't take very long. Okay, all right, I'm gonna keep going. All right, number 4 and 5. All right, these are just reading things that are given to us. Okay, so in 1 and 2, we came up with our own sign charts. This time we're being given sign charts, and we're going to see what to do with them. Okay, so we are given a bunch of different things. We're given a table for one thing. We're given a bunch of limits, and then we're given sign charts for f prime and for f double prime. And it's a lot of stuff being thrown at you, but I'm going to show you what each one of these mean. So first off, the simplest thing is tables. Tables will give you points. So if I have this table like x on top and f of x on the bottom, just look at each of these pairs. So I have the point 0, 1. That's going to be on our curve. I have the point 2, -2, and 3, -1. So those are the 3 points that are going to be on our curve. Okay, so tables give us points. All right, next thing, we have a limit at plus or minus infinity. So look at this, look really close. So this is going to plus or minus infinity. Those are horizontal asymptotes. Okay, so that's showing you what happens as we go way off to the left and right. And so this is going to give us y equals 0. So this equals 0. This horizontal asymptote is y equals 0. So as we go off to either side, we're going to be approaching a height of 0. That's what that means. Okay, we have other limits here. So we have a limit as we approach 1 from the left, so that's this negative, and from the right, that's the positive. All right, and in either case, we're going up to infinity. So at x equals 1, when we come in from the left, we're going up to infinity, and when we come in from the right, we're going up to infinity. So this is what it's going to look like at x equals 1. All right, so that's what it's telling us. So there is a vertical asymptote at x equals 1. And so we'll draw this in later. For the sign charts, we have for f prime tells us if it's increasing or decreasing. Okay, so plus means it's increasing, minus decreasing, plus increasing. Simple. Okay, so we do have here, looking at these 2 critical points, this one says ND. That means not defined. Okay, so there's not going to be a minimum or a maximum here. Not defined means there's nothing there. It's just a hole. And that's actually where the vertical asymptote is, at 1. Okay, but this other one, this other critical point, so as we go from decreasing to increasing, that's a minimum. So that's the first derivative test. We go from decreasing to increasing, it's minimum. So there's a minimum at x equals 2. But the question is, like, what is the actual point? And we get that from the table. We know there's a minimum at 2. This table tells us what that actual point is. So for x equals 2, we have a y value of minus 2. So we get this point 2 minus 2. That's going to be our local minimum. Okay. For the second derivative chart, this is telling us whether it's concave up or concave down. So where it's positive, that's concave up. So up here, it's concave up here in the middle, and then it's concave down on the right. All right. And then an inflection point occurs wherever these change. So like over here, we're going from concave up to concave down. So in the middle here, that's an inflection point at x equals 3. And then to get from this to the y value, you just look back at your table. So we know that for x equals 3, our y value is minus 1. And so we get the inflection point 3 minus 1. Okay. So the sign charts are only going to give you x values, but to find the y value, you're going to use the table. So it's just a bunch of things that you have to bring together in order to answer this question. Okay, number 4, this is just like number 1. We're going to write out the intervals. So if we look at the first derivative for increasing and decreasing, it's increasing on the left and the right. So that's minus infinity up to 1, union 2 up to infinity. All right, so these are the left and right intervals. And then it's decreasing in the middle here from 1 to 2. Local maximum, there is none. Thanks. And there's none because this is not defined here. There's an asymptote here. Like I said, we're going up to the asymptote. So there's no actual point there. So we don't have a local max. But the local min here goes from decreasing to increasing. That's the first derivative test. We have a local minimum at 2 minus 2. Okay. And these are intervals, these are points, so you need x and y. Okay, so yeah, once you know how to read these, this will only take you a couple minutes to fill out. We're going to do the same thing for number 5. So number 5, concave up. That's wherever this is positive. So there's kind of a trick here that you need to pay attention to. So we have these 2 intervals right next to each other that are positive, right? So this left one and this middle one, They're both positive. So it might be tempting for you to write minus infinity all the way up to 3. Like you just skip over this middle point. You can't do that. So you have to leave this hole out, right? So this not defined point, you have to leave it out. And so the way we do that, we say it's concave up on the left part, that's minus infinity up to 1. And then we say union, the middle one, which is 1 up to 3. Okay, so what I've done here is I've left out the 1. So I have these open endpoints here. The 1 is not included, right? So it's important that you do that. Okay, for concave down, that's just where it's negative. So that's 3 up to infinity, the right segment. Okay. Inflection points, that's where it's changing from concave up to concave down, or the other way around. So there's one at 3, minus 1. We get that from the table. Okay, so we're done with the sign charts. Now we look at the asymptotes. So back up here, this limit at plus or minus infinity, this gives us a horizontal asymptote. So it says it's equal to 0, so we just have y equals 0. For this other one, we have the limit as we're approaching 1, that's blowing up. So we're blowing up to infinity at x equals 1. So we have a vertical asymptote at x equals 1. Okay. So all we're doing is we're just reading all of these things and writing them down. Okay. So any questions on 4 and 5? We're going to use this again in a second. If they don't equal, is there no vertical asymptotes? Oh, right. So like if we had x approaches 1 and like x approaches 2, those are two different things. You would actually be given 4. You'd be given 4 limits here, right? So you need to have a left and a right for each one of these vertical asymptotes. So right, we have a left and right for 1. So if you had another vertical asymptote, like at 2, you'd have a left and a right for 2. Let's see, why 1? Why is it 1? Okay, so as we're approaching x equals 1, I'll show you this in a second because we're going to graph it. But as we're approaching x equals 1, our graph is going up to infinity on both sides. And so that's a vertical asymptote, right? So when we're approaching plus or minus infinity, that's horizontal. When we're approaching some number, right, like 1, 2, 3, that's a vertical asymptote if it's blowing up. And I'll show you in a second. But anyway, if they don't equal, okay, so if this one's positive infinity and this one's negative infinity, that just means from the left, we're going up, and from the right, we're going down. And this might be flipped if you're looking at me. But that's still an asymptote, still vertical asymptote. Now we're going to go to number 6, drawing the actual graph. Okay, so same as before, I'm just gonna start out and put down all the information that we have. So from the table, we're going to get different points on the curve. From the limits that we had, we're going to get some vertical and horizontal asymptotes. And I'm also going to draw arrows to show which direction that we're going. And then from the sign charts, that's going to tell us like where the local min and max are, where the inflection points are. And these things are all going to be useful. So I'm going to show you now exactly how I would construct this graph. So first of all, we're going to look at the points. I'm going to put down my points. So we look at our table. We have the point 0, 1. So I'm going to draw a point at 0, 1, right there. Okay. I also have the point 2, minus 2. So that's 2, go down 2, right there. And then I have a point at 3, minus 1. So I'm going to draw on all these points, 1, 2, 3. Okay, so I put down all the points from the table. Now I'm going to draw on my asymptotes. So step 2, I'm going to draw on the asymptotes. So we have a horizontal one at y equals 0, like we had before. So as we go out to the left and right, we're going to be approaching a height of 0. Let me draw that in. All right, so that's this dotted line here. And as we go out to the left and right, we're going to be approaching this line. So that's why I'm drawing little arrows here. Okay. All right. For the vertical asymptote, we have x equals 1. Right, so we're given a number 1 here. So I'm going to draw this dotted line x equals 1, a vertical line. All right. And now the arrows are actually pretty important for this one. So as we approach it from the left, that's this 1 minus, the minus sign here. As we approach it from the left, we're going to be going up to infinity. All right, so I'm drawing an arrow here. As we come at it from the right, we're also going up to positive infinity. All right. So in either case, we're going up to infinity from the left and the right. Okay, and then that's it. That's it for now. All we have to do now is connect the dots. So connect the dots that we have and approach the asymptotes. And then we're going to check and make sure that it makes sense. Okay, so we need to draw a line that's going to approach these lines, approach these asymptotes, and connect through these dots. Oh, one last thing. From these sign charts, this is going to help us. We have a local min and max and inflection points. So let me just label those real quick. So like we had before, we found out that this point is a local minimum. So 2 minus 2, what we had before, is a local minimum. And then 3 minus 1 is an inflection point. Okay, so I'm just going to label those for my sake. All right. And so real quick, what a local minimum is going to look like, it's going to look like a U, sort of. We're going to go down and then come back up. All right. And so that'll help us in a second. All right, so I'm going to connect the dots and approach the asymptotes. So I'll start out very close to this line. And then I'm going to turn, come up through this point, and then approach this vertical asymptote, right? And that looks horrible, but I have a pre-drawn one here, just so that it looks a little bit nicer. Right. So we're going to start out very close to this horizontal asymptote, pass through this point, and then approach the vertical asymptote going upwards. Okay. Next thing is we have to connect through these 2 points. So we come off of this vertical asymptote. We have to connect through these 2 points and then approach this horizontal asymptote. And so the way we can do that is we come down. We know that because this is a local min, we're going to turn around here. All right. And then what an inflection point is we're going to shift from curving upwards to curving downwards. Right. So in here, we're bending upwards. And then over here, we're bending downwards. So it's a change in concavity there. And after that, we're approaching this horizontal asymptote. Okay. And so I have a little bit of a nicer drawing here. Okay. So this local minimum, right? That's the very bottom. It's kind of shaped like a U. This inflection point, we're changing from curving down. Okay. So all we did is connect the dots and approach these lines. Okay. And then all that we have to do now is just check and make sure that this matches with the sign charts that we have. So we know that between minus infinity and 1, this is going to be increasing. So everything on this left here, this needs to be increasing, which it is. It's going to be decreasing in the middle between 1 and 2. So here's 1 to 2, that's decreasing. And then it's going to be increasing here on the right. Okay, so that's what we wanted to see. And then for the second derivative, that's telling us whether it's concave up or concave down. So it needs to be concave up on this left interval, which it is. You see it's bending upwards. It needs to be concave up between which you can see it is, right? So it's scooping upwards. And then it needs to be concave down from 3 on. So once we get to 3, we need to be bending downwards. Let's see. So there's a good question here, which is how can a line go through the asymptote? I'll just tell you real quick. Lines can never go through a vertical asymptote. Lines will never go through a vertical asymptote, but they can go through a horizontal asymptote. So all the horizontal asymptote is telling you is that as you get really, really far out, you're going to be approaching this line. It doesn't tell you anything about what's happening in the middle here. So for horizontal asymptotes, all you have to do is approach it off at the left and the right. So you can go through them. You just have to approach them at the left and right. But for vertical asymptote, you're never going to go through it. Sorry, does that answer your question? Yeah, so don't be afraid if you come up with something that ends up passing through this horizontal asymptote. All you have to do is look at the long-term behavior. All right, cool. Okay, if y'all have any like more questions or you want more details about that, I have like another example drawn up here that you can look at when you're reviewing. But okay, any questions on number 6? All right, so we're going to connect the dots and try and approach these asymptotes. Okay. All right, so yeah, this is a big one. There's a lot of thinking to be done here. Okay, so make sure you practice that. Okay, 7 and 8. Let's keep going. 7 and 8. These are about absolutes, absolute max and mins. So these are the highest and the lowest points in an interval. So previously we were looking at just locals, so which means like a point that's higher than the others nearby. But now we want the point that's the highest out of all of the functions, or sorry, out of all the points in the function. So I'm just going to tell you how to do it. So step 1 is always to get the critical, because we're always going to need to look at the critical points. And then you have 2 different things to consider. Okay, if your interval is closed, you need to test it at 3 different points. So the endpoints and any critical points that there are. So I've kind of drawn a picture here. So you see these 3 different points. So at the endpoints and at this critical point, the absolute max and min are going to occur either at the endpoints or at this critical point. Okay, so you need to test just those 3 points. That means just plug into them and see what values you get. Right? The highest value is going to be the maximum, and the lowest value is going to be the minimum. All right, so that's if you have closed. If you have closed, you test A, B, so the endpoints and the critical points. If it's open, you're just going to test at the critical point. Okay, so you're just going to look at the critical point, not at the endpoints. And then in order to determine if it's a maximum or a minimum, you have nothing to compare to. You have to have another way of determining if it's maximum or minimum. And you do that by looking at the second derivative. So if the second derivative is positive, that means it's curving upwards. You're looking at a minimum. And if the second derivative is negative, which means it's curving downwards, you're looking at a maximum. So again, it's like a valley and the top of a mountain. Right, so that's how you determine it. That's called the second derivative test. So you just look at the sign of the second derivative. Positive means a minimum, and negative means a maximum. Okay. All right, and so let's work on 7 and 8. So for 7, it wants us to find the absolute max and min of this function on the closed interval, -3 to 2. So this means it includes the numbers 3 and 2. We're always going to start out by getting the critical points. So we have to take the derivative. First term gives us 2x. Second term gives us a 4. I'm going to factor that. I'm going to pull out a 2. So we have 2 times x plus 2. And that will give us x equals -2. Okay. And now because this is closed, I have to test at the endpoints and the critical point. Okay, so all I'm going to do is plug in the endpoints. So -3 2, and the critical point, which is minus 2. So I'm going to plug in all these points and see what numbers I get. So how high these points are. So I plug these into f of x. So f of minus 3, that gives me 0. F of minus 2 gives me a minus 1. And f of 2 gives me a 15. So I found the height of all of these different points. The highest one is the maximum, and the lowest one is the minimum. So the absolute max here is at f of 2. So f of 2 equals 15. That's the highest. So I can write that either as f of 2 equals 15 or as the point 215. And then for the minimum, that occurs at minus 2. So f of minus 2 equals minus 1. Or I can also write that as the point minus 2 minus 1. Okay, so closed intervals, you test at the endpoints and critical point. Okay, that's it. Highest is the max, lowest is the min. Any questions on this one? Okay. If it were open, do you do the second? Yes. So for number 8, we have an open interval this time, so we're going to do the second derivative test. So number 8, we have a different function, x squared minus 4x minus 7, on the interval 0 to infinity, and these are open. So we don't test the endpoints that are open. We're going to need to use the second derivative test instead. All right, so as before, we're going to get the critical point, right? So we take the derivative, we get 2x minus 4. Then I factored this out. So we have 2 times x minus 2. And that gives us x equals 2, right? That'll make it 0. So this is a critical point at x equals 2. All I have to do now is find the value there. So f of 2, plug in a 2, I get minus 1. Right, so I have the point 2 minus 1. And the only question is it a max or a min? And take the second derivative and see what I get. So if I look at f, I take one more derivative here. All I get is 2. So this first term gives me a 2, and that's positive, right? So that means f is curving upwards. So this is a minimum. Okay. All right, and so I write it like this. The absolute minimum is at f of 2 equals minus 1 or 2 minus 1, 2 comma minus 1. Either one will work. Okay. So that was kind of quick. Any questions on this one? Why does f of x have a plus 3 in the equation when you plug the point in instead of minus 7? Oh, that's a good question. Sorry. Yeah, did I read that? Oh yeah, I was using the previous function. Good catch. So this is 4 minus 8 is minus 4 plus 7. I think that should be positive 3. Let me check.
It's minus 7.
Oh yeah, my bad. Minus 7. So this is minus 4 minus 7 is minus 11, and that's what you get on the test or on the answer key. Thank you. But yeah, everything holds the same except this is a minus 11 and then 2 minus 11. Sorry. Okay. So yeah, y'all caught that. Good. Okay. So any questions on how to do this? So for open, you find the critical point, get the point there, and then the second derivative test will tell you if it's a max or a min. Okay. All right. All right. Number 9 and 10. These are word problems. So number 9 has a really easy trick to it. It's something that we've done already a couple times. Okay, a baseball cap manufacturer is planning to expand its workforce. It estimates the number of caps produced when X new workers are hired to be this function right here. So T, this number of caps produced, and that's between 0 and 15 workers. Okay, how many workers is the question? How many workers should be hired in order to maximize the rate of change in cap production? The point of diminishing returns. Okay, so there are a lot of words here. But what the question is asking for is how many workers do we need to reach the point of diminishing returns? Okay, and all you need to know is that the point of diminishing returns is the inflection point. Okay, that's the point at which your rate starts decreasing. Okay, so drew a little picture here. So this x-axis is the number of workers that we have. The y-axis is the number of hats that we're making. So 0 workers, starting out here, 0 workers, we have 0 hats. Okay. Over here at about 15 workers, we have like about 4,100 hats or so that are being made. And then any workers that we add beyond that brings us back down. But actually we only care about between, we care about between 0 and 15. So just like ignore this right side. Let me actually crop that off. So we care about numbers between 0 and 15 because it doesn't make sense. Like if you add more workers, you're not going to go back down. But anyway, this inflection point here is what we're looking for. So as we add more workers, we get increasingly good returns. Like our slope, our rate keeps increasing up to this point. And then after this, it starts to flatten back out again. So we're going from curving upwards to curving downwards. This is the point of diminishing returns. So we've done this before. All we have to do to find the inflection point is set the second derivative equal to 0. Okay. Okay. Step 1 is to get the second derivative. So this is our function. Taking the power rule on this, so the 4 comes down. So we get a minus x cubed. Second term gives us a plus 15x squared. All right, that's our first derivative. And then for the second derivative, we do this again. So this is going to give us minus 3x squared. Second term will give us a 30x. All right, that's just power rule. Okay, and this is all equal to, so I factored it here. Let me actually rewrite this. So this is all equal to 3x times minus x plus 10. And we're going to set that equal to 0. Okay, so I factored it and set it equal to 0. And so by factoring it, it's really easy to see what we need. Okay, so we have x equals 0 is one of the options, and x equals 10 is the other option. So 0 workers and 10 workers. We're going to focus on 10. So ignore the 0. Right. So at 0, we don't have any workers yet. Like we haven't reached a point of diminishing returns because we haven't gotten any returns yet at all. So just ignore the 0. We're going to be focusing on x equals 10. Okay. So this is obviously, this is going to be our answer. This is the point of diminishing returns, but we do have to show one more thing. We have to show that our sign chart goes from plus to minus. So what that means is we're going from curving upwards to curving downwards, like you see here. That's what a point of diminishing returns looks like. So we want to show that. Okay, I'm going to use the Mrs. Seats method here, which is to look at the terms, 3x and minus x plus 10. Okay, and so in each of these intervals, we're just going to see what the sign is. So between 0 and 10, 3x is positive. So if I plugged in 1, I'd get 3. 10 and greater, this is also going to be positive. So if I plugged in like 11, I'd get 33, positive number. For minus x plus 10, if I pick something less than 10, I'm going to get a positive number. So like if I picked 9, I'd get minus 9 plus 10, which is 1. So I'm going to get a positive number here. And then if I pick a number greater than 10, this will be negative. Okay, so this is how Ms. Seats does it. She just looks at the terms individually. On the left, they're both the same sign, so that's positive. And on the right, they are opposite signs, so that's negative. So when you multiply them together, you're going to get a negative number. Okay, and at this point, you've shown everything that you need to. So the second derivative goes from positive to negative. You're good. Okay, and so the answer to the question is the optimal number of workers to hire is 10. Okay. All right, so why do we ignore the 0? Okay, so there's actually another reason why we ignore the 0, which is that our range only goes from 0 to 15. So let me cut this off so you can see it. Right, we're going from 0 to 15. there's not a change of concavity here because we don't have anything on the left. We don't have anything to change. So we're not going from up to down, right? But another reason is like zero is not telling us anything. Like we want to hire some number of new workers until it stops giving us as good returns. If we stop at 0 workers, that's not going to give us anything reasonable. All right, so just focus on the one that's non-zero for this. Like consider like what's actually happening in the problem. Okay, is the right side always going to be negative because it is diminishing? Yes. So you're going to need to show this because Ms. Seats wants you to real quick. But yeah, this is just what a diminishing returns point looks like. So we're trying to get the highest slope, the highest rate, and it's highest right here before we start leveling off. It's highest at this inflection point. Okay. So another way that you can look at this is this is the first derivative. This is the derivative of the first derivative. All right. So if you were to think about this as your rate, the first derivative of your rate, you'd say that your rate is increasing here, and then your rate is decreasing here. And so because of that, the rate is a maximum in the middle. So that's the first derivative rule. Okay. Sorry if that was kind of long-winded. All that we have to do is find the inflection point and then show that the chart goes from plus to minus there. Okay. So that's all you need to know for the test. Okay. Any questions on this one? Okay. One more. This one has a nice trick to it. This is something you haven't done before. Okay. So all units of a 300 unit apartment building are rented when the monthly rent is $1,000. A marketing survey indicates that for each $40 increase in price, 1 unit becomes vacant. Write the revenue function and determine the rent price that will maximize the revenue. So I think this will probably be the hardest problem, aside from the graphing on number 6. I think this will probably be the hardest problem just because of all the steps that you need to take. Okay, but it really just boils down to something simple, which is that you have to come up with the variables and the functions yourself. All right, once you do that, it's just the same as the other problems, but you have to come up with the functions yourself. So I'm going to try and explain exactly how you do that. Okay, so let's try and understand like what the problem is saying. We have an apartment building. The rent is at $1,000. And we have 300 rooms that are occupied. So the idea that's going on here is every time we raise the price, so like if we go to $1,040, one person is not going to be willing to live there anymore. All right, so this is like supply and demand. If we go $1,040, we'll only have 299 apartments filled. If we go up to $1,080, we'll only have 298 apartments filled. Okay, so every time we jack up the price, one person moves out because they're not willing to pay it anymore. Okay, so that's what's happening. Now what this is asking for, it's telling us to write the revenue function and to determine the rent price that's going to maximize it. So first thing we need to get is a revenue function. Now how do we get a revenue function? Revenue is price times units. Right, so it's the price of the things that you're selling times the number of things that you sell. So it's like your total income. But the first thing we have to do is we have to figure out what our variable is going to be. What is the thing that we're going to change? We have to come up with our own variable. And this is it. This is the thing that's changing. For each $40 increase in price, 1 unit is going to become vacant, and our price is going to increase by $40. So this is what's changing. Each increase in price, this increase here. So like if you see this, if you see increase or decrease, that's probably a good sign that that's what we're talking about. And so this is exactly what I'm going to pick. I'm going to say that X is the number of $40 increases. All right, that might be confusing. It's just the number of times that we're jacking up the price. Okay, so for example, at x equals 1, that'll mean that I jacked it up once. So I added $40 to it. So the price is going to be $1,040, and the number of units is going to be 299. That's just what the problem tells me. So price goes up and the number of units occupied goes down. Okay, so this is probably the hardest step, just figuring out what this is going to be. Okay, next step is to figure out what this price function and the number of units function is going to be in terms of x. So the price is easy. We start out $1,000, and then every time we jack up the price, it's going up by 40, right? So it's going up by $40 each time. So the price is 1,000 plus 40x. Okay. Now the number of units, 300, and then every time we jack up the price, it goes down by 1, right? So it's 300 minus x. Okay. And now once you have these, you're all set. We know what to do from here. So the revenue function, that's just your price times the number of units that you have occupied. Okay, so you just take these two things and multiply them together. That's your answer. What I've done from here is I've pulled this out so that we can take the derivative more easily, because we're going to do that in a second. But this is just price times unit, and that's one of the things it's asking for. Okay, and now in order to find the maximum, so it says we're trying to maximize the revenue here. In order to maximize this, you have to find the critical point. And we've done that before. We just set the derivative equal to 0. So take the derivative, that's 0. This gives us 11,000. The last one gives us minus 80x. Okay, set that equal to 0 and solve. We get x equals 137.5. Let me just do that on your calculator. Okay, so we have the critical point. Now we have to show its maximum. So we're going to do the second derivative test again. All right, so all we do is we take the second derivative. We take one more derivative, and we get minus 80. Okay, this means that the function is curving downwards here, right? And so the critical point that we have is going to be on top. It's going to be a maximum. All right, so second derivative is negative. That means this is a maximum, and that's the second derivative test. Okay, so that's it. We have x, we have x, we have x. That's the number of times we're increasing. The last thing to do is get the corresponding price here. So we just plug this x back into our price function in order to see what the actual price of the units is going to be. So we started out 1,000. We did 137.5 price increases, so $40 each. So that put the price up at $6,500. Okay, so just plug back into the price function to get the price. And we're done. Okay, so we had the revenue function, that's what I was asking for here. And the optimal rent price, which we just found, is $6,500. Okay, so the hardest steps that you're going to need to take here is to figure out what x is and to figure out what these functions are. And it all depends on what the problem is telling you. Okay, so you have to really understand what the problem is asking. In this case, it was like a supply and demand problem. Okay. All right, so are there any questions about number 10? Or about any of the other questions on the practice? Okay, if not, I'm going to send this out to everybody, and y'all are free to go. I'm going to stick around here for a second and answer any questions on quiz 9. Some people asked for that, but yeah, thank y'all for coming. Not bad time on this one. So good luck tomorrow. Good luck tomorrow. Make sure you review this. I'll send this out. I also graded your quiz 8. So if you made any mistakes on that, make sure to check those. But yeah, okay. Y'all have a good day.
Thank you.
You're welcome. Good luck tomorrow. All right, and I gotta send those links out to everybody. You're welcome. Okay. All right. Now I know that some of you had questions on quiz number 9. So give me a second to pull that up and we'll look at that.